This resource is the third in a 6-part series on exponents and logarithms. Part 1 defines exponents and logarithms. The exponent laws are defined, and justification for the exponent law of multiplication is provided. We consider how to transform between exponent notation and logarithmic notation, and define two special bases for logarithms. Part 2 explores expanding and contracting logarithms. Multiple examples of each are provided. Part 3 demonstrates solving logarithmic equations, with examples provided. Part 4 considers solving exponential equations. A general solution method is provided, and examples are given. Part 5 delves into solving exponential growth equations, with examples. Part 6 looks at solving exponential decay equations, with special emphasis on half-life problems. In solving logarithmic equations, we take the logarithm of some variable expression and have that equal to some constant. There may be only one visible logarithm, or several. The methods we will use to solve these logarithmic equations will differ depending on if there is one log or multiple. After solving, there is one potential problem. Logarithms are only defined for positive values, so you need to double check that your solution keeps the original variable expression positive. Let's see how to solve a basic logarithmic equation. A basic logarithmic equation only has one logarithm. This means you need not worry about contracting the logarithm. But what is the process for solving this type of equation? First, make sure that your equation is in the format of log base b of some variable expression m equals c. We may need to do some algebra to make the equation fit this format, but that should not be too large a task. Next, use the definition of a logarithm to transform the equation into its equivalent exponential form. Since our variable expression is the m, we should have numbers for the b and the c. We will simplify this b raised to the c exponent. Then solve the equation we have remaining. Finally, check your answer to make sure that the original variable expression is greater than 0. Let's look at an example. Suppose we have the logarithmic equation log base 2 of x minus 4 equals 3. We are already in the correct format, so we can transform the logarithm into its equivalent exponential form. The problem becomes 2 raised to the third power equals x minus 4. We can simplify the exponent, as 2 to the third power is 8. We want to get the x all by itself. To eliminate the minus 4, we will add 4 to both sides of the equation. This leaves us with our answer, x equals 12. We need to check that our original variable expression results in a positive number. Our original variable expression was x minus 4. Since we found x to equal 12, we subtract 4 and get 8. Since 8 is positive, our solution is valid. But what happens if we have multiple logarithms in our equation? What if our equation has multiple logarithms? There are two cases. Either the logarithms are on one side of the equal sign, or they are not. First, we consider the case where the logarithms are all on one side of the equal sign. First, we want to contract the logarithms into a single log. Then we proceed as before. Make sure the logarithm is in the proper format. Rewrite as the equivalent exponential equation. Simplify the exponent. Solve appropriately. Check that our answer results in positive values for all variable expressions. Let's look at an example. Suppose we want to solve the equation log base 6 of 2 plus log base 6 of the quantity x minus 7 equals 3. While there are multiple logarithms, they are all on the left side of the equal sign. we will contract the logs. Recall that a sum of logarithms is the same as the logarithm of the product. So we are left with log base 6 of 2 times the quantity x minus 7 equals 3. We can transform the logarithmic equation into its equivalent exponential form. Doing so, we have 2 times the quantity x minus 7 equals 6 to the third power. Distributing through the parentheses on the left side of the equal sign leaves us with 2x minus 14. Evaluating the exponent, 6 raised to the third power equals 216. We are left with a relatively simple linear equation. We want to isolate the variable term, so we add 14 to both sides of the equation. This leaves us with 2x equals 230. Divide both sides by 2, so x equals 115. Checking our original variable expression, 115 minus 7 is clearly positive, so we have found our solution. We will consider the case where our equation has logarithms on both sides of the equal sign. First, we want to contract the logarithms on both sides of the equation, so there is only one log per side. Then we raise the base of the logarithm to each side of the equation. Because we have the base of logarithm raised to the logarithm itself, they cancel each other out. We will be left with an equation that we can solve using the appropriate method. Let's look at an example. Suppose we have the logarithmic equation, common logarithm of the quantity x minus 3 equals the common logarithm of the quantity 7x minus 23 minus the common logarithm of 5. How could we solve this? Because we have multiple logarithms on the right side of the equation, we would first contract that side. The subtraction of the logarithms becomes the log of the quotient. So now we have log of x minus 3 equal to the log of 7x minus 23 divided by 5. We want to eliminate the common logarithm from the equation. Recall that the common logarithm is really the base 10 logarithm. So to eliminate the common log, we raise 10 to the power represented by each side of the equation. So we have 10 raised to the power, the common logarithm of x minus 3 on the left side of the equal sign. On the right, we have 10 raised to the power, the common logarithm of 7x minus 23 divided by 5. Because the common logarithm and 10 raised to an exponent are inverse functions, they cancel each other out. We are left with x minus 3 equal to 7x minus 23 divided by 5. To solve this equation, we first multiply both sides by the 5 to get rid of the fraction. We are left with 5 times the quantity x minus 3 equal to 7x minus 23. Distributing through the parentheses, we have 5x minus 15 equal to 7x minus 23. Now we want to isolate the variable on one side of the equation. We subtract 5x from both sides of the equation and are left with negative 15 equal to 2x minus 23. We want the constant number on the opposite side of the equation from the variable. We add 23 to both sides of the equation. We are left with 8 equals 2x. Dividing both sides by 2, we get 4 equals x. Checking our original variable expressions, 4 minus 3 is positive 1, and 7 times 4 minus 23 is positive 5. So our solution lies within the domain of the logarithmic function. So we are done. A logarithmic equation involves taking the logarithm of a variable expression. If there is only one logarithm statement, the basic process for solving is to rewrite the logarithm as its equivalent exponential form. This results in an equation that can be solved by normal means, hopefully some manner of linear equation. If there were multiple logarithmic statements that were all on one side of the equation, first we want to condense those statements into a single logarithm. We then proceed as before. If, however, there are logarithms on both sides of the equation, condense both sides. Then we effectively get to drop the log, as we take the statements on each side as an exponent for the logarithmic base. We solve the resulting equation in a normal fashion. No matter the original problem, after solving the equation, we have to ensure that the solution makes sense. The original variable expression must be positive. But what happens if the variable we are trying to solve for is the exponent? We will consider these exponential equations in the next installment of this series.